Okay, so this is not one of the suggested problems from chapter 3, but I think something very similar was in the homework and it came up a couple of times in class, so I want to go over. This is problem 63. And it's relatively simple, but simple is good. Simple is good that we can actually expose some fundamental ideas. We have a person in a passenger basket of a hot air balloon throws a ball horizontally outward from the basket with a speed 10 meters per second. So first of all, they are talking about the velocity with respect to the balloon, and not velocity with respect to the ground. This is kind of clear from the way they are talking about. What initial velocity, magnitude, and direction does the ball have relative to a person standing on the ground? Now, it's of course very clear. If they were already giving this, then they would be asking for it. A, if the hot air balloon is rising at 5 meters per second relative to the ground during the throw, and B, if the hot air balloon is descending at 5 meters per second relative to the ground. Okay, so we have some hot air balloon, and we have some rock that's being thrown. Okay? So this is the velocity of the rock with respect to the balloon. This is 10 meters per second. And we have two cases. Either the balloon is rising, okay? So the velocity of the balloon with respect to ground, let's call this 1, is rising at 5 meters per second, or it's coming down, velocity of the balloon with respect to ground 2 is 5 meters per second. Okay? So these are two cases. What will be the velocity of the rock with respect to the ground? This is the question. Okay? Now, velocity of the rock with respect to ground is going to be the velocity of the rock with respect to the balloon plus the velocity of the balloon with respect to the ground. So this is going to be velocity of the rock with respect to the balloon plus the velocity of the balloon with respect to the ground. And you can tell that this works because, as I indicated in the class, when you write it this way, if there are neighboring indices, they just collapse. So this becomes VRG, which is what we are looking for. Okay? If one of them was opposite, then we will just revert this and put a negative sign in front of it and solve the problem this way. But we don't need it here because we're already given the velocity of the rock with respect to the balloon and the velocity of the balloon with respect to the ground for the two cases. Okay? Now, what will this look like? This is an application of vector addition. In the first case, for part A, we have two vectors. One is of size 10, one is of size 5. And when we add them up, we're going to get something like this. Okay? So this is the velocity of the balloon with respect to ground. Let's call this 1 again. This is my vector. And the velocity of the balloon with respect to ground, 1, the magnitude is going to be 5 square plus 10 square square root. Now, to indicate its direction, we should say that, it makes an angle theta above the horizontal. And what's that theta? Well, tangent theta is 5 by 10. This is a right triangle. So this is horizontal motion, this is vertical motion. They are, of course, perpendicular to each other. This is a right triangle. That's how I use this Pythagoras theorem to get the length of the hypotenuse. And this is just a half. So it's arctangent of 1/2. Okay. Now, for part B, we are going to have sort of the opposite case. We have 10 this way and 5 that way. So theta degrees above horizontal, I would write, if you want to indicate the direction. And here we get something like this. Everything is going to look the same, but this time we are going to get theta degrees below horizontal. Okay? And it's just the same triangle reflected downwards. And this is how I would answer this question.